Node3, 2022, January 25, dispatch B+. It was about an hour and a half total. And this is the Perimeter Institute from Canada. This is the only reason I am sharing this way is because I could not find any other method by which to share it online. And I imagine there's a lot of people out there who don't have any access to Roku or something like it. But the necessity for calibration in science is such that if it's really bad, they'll send me a C&D letter asking me to remove it, and I will. So, without further ado, enjoy this as I fold space-time as the limit approaches the volume encompassed by my laundry.
On this edition of Celebrating Science, a special panel discussion about the physics of information. Brought to you by Canada's Perimeter Institute for Theoretical Physics, an independent, non-profit scientific research and education outreach organization, home to a growing cluster of international scientists who contemplate and calculate new ideas about the very essence of space, time, matter, and information. Perimeter Institute also offers a wide array of educational outreach activities for students, teachers, and members of the general public in order to share the joys of scientific research, discovery, and innovation. In tonight's edition, recorded for radio, 4 noted scientists take part in a panel discussion on the fundamental essence of information and how it applies to some of the most complex questions in modern physics.
Good evening, ladies and gentlemen. Welcome to Perimeter Institute's public event series. My name is John Matlock. I'm the director with the Institute. It's my pleasure to welcome you here and to all of the audiences who are tuning us in around the globe electronically. We have a very special presentation on the physics of information. We have a special format, special host. He is Bob McDonald of Quirks and Quirks. Bob is one of Canada's best-known science journalists. He's not only been the host of Quirks since 1992, he has an extensive history in communicating science. This includes his broadcasts on CBC Radio Ideas, As It Happens, and Morningside. On CBC Television, Bob was the host of the children's program Wonderstruck, and we continue to see him on The National, where he is the national science correspondent. In addition to his work with CBC, TV Ontario, and other broadcasters, Bob has written for the Globe and Mail and has written several popular books. He's received several honors for his contributions in science communication, including having received the Michael Smith Award for Science Promotion from NSERC, the Sanford Fleming Medal from the Royal Canadian Institute, and the McNeil Medal for the Public Awareness of Science program from the Royal Society of Canada. He also holds a number of honorary degrees from Laurentian, the University of Guelph, and Carleton. Ladies and gentlemen, please welcome to Perimeter Institute's stage, Bob McDonald.
Good evening, ladies and gentlemen. Wow. I'm Bob McDonald, host of Quirks and Quirks, our national science program on CBC Radio. Perhaps you've heard of it. I'd like to welcome you to this very special Perimeter Institute presentation. This evening's discussion is called The Physics of Information, What the Universe Doesn't Want You to Know. And let me begin by introducing our very distinguished panel. On my far left, Dr. Chris Fuchs, a long-term visitor at Perimeter Institute who specializes in quantum information and quantum foundations, and he's also an adjunct professor of physics at the University of New Mexico. Next to him, Dr. Tony Leggett is a professor of physics at the University of Illinois and the 2003 Nobel laureate in physics for his work on superfluidity. He also was a member of Perimeter Institute's Scientific Advisory Committee, and more recently he was named the Mike and Ophelia Lazaridis Distinguished Research Chair at the University of Waterloo. On my right, your left, Dr. Seth Lloyd, a quantum computer engineer and a professor of mechanical engineering at the Massachusetts Institute of Technology, and Dr. Leonard Susskind, a professor of physics at Stanford University and associate faculty member at Perimeter Institute. Ladies and gentlemen, this is your panel for this evening. Now, if you've attended other Perimeter Institute events like this, or occasionally listened to Quirks and Quarks, you know something that most people have figured out. Physicists are not like the rest of us. I know, they look like normal human beings, but they don't see the world the same way that we do. Take information, for example. When you or I have a question, what do? We look it up. You go to a book, you go to the internet, you ask somebody, the information is just data that's out there, all you have to do is find it, or maybe share it with someone else. But that's not how physicists view information. They want to know what the information itself is actually made of. So imagine you're looking up information on a website. Now to you or I, we just see the details that are on the screen. But suppose you could look inside your computer with a really powerful microscope. Now you see the actual bits of data moving through the wires and the circuit boards. They're individual kernels of information. And these bits are being manipulated. And they're being transferred here and there as tiny little electric charges. Or you can look at an apple. Not the kind you type on, but the kind you eat. You might take a bite out of that apple, and you'll see a bite. But a physicist sees a bit. Or millions of bits. And those bits define the apple. Its shape, its color, its texture, its very existence can be defined as bits of information. So this idea that information and physics are intimately related has involved some of the world's greatest scientists in long-running intellectual debates. And their ideas on the physicality of information provide deep, though controversial, insights into some of the hardest problems in modern physics, including our understanding of the universe, one of the smaller problems we have, black holes, and paradoxes that you find in quantum mechanics. Their research is also leading to new technologies to calculate, to store, to transmit information in quantum computing, quantum cryptography, and quantum teleportation. Beam me up, Scotty. So let's get down to the nitty-gritty and see what information we can glean from our guest today. And I'd like to start with Dr. Seth Lloyd from MIT. Now, most of us see information as something that you just read or you copy or you share with somebody else. What's that got to do with physics?
Well, everything. Sorry, did you want a longer answer?
A little longer. This isn't the news.
So Bob, actually, 150 years ago, people weren't so concerned about information because they weren't living through an information processing revolution. But 150 years ago, a bunch of physicists, James Clerk Maxwell at Cambridge and Edinburgh, Ludwig Boltzmann in Vienna, Josiah Willard Gibbs at Yale, they actually discovered the fundamental formula that described information. And they didn't describe it in terms of bits. They discovered that formula because they were looking at how atoms move around. And they wanted to quantify this funky stuff called entropy. Now, entropy was at that time known as a quantity that gummed up the works of heat engines, of steam engines, and kept them from doing the amount of work you'd want them to do. But phrased in modern terms, what Maxwell, Boltzmann, and Gibbs discovered was that entropy is actually information. It's bits. So these atoms, as they move around, they carry bits of information with them. And every time two atoms collide, those bits flip. So in fact, not only does information have everything to do with physics, but physicists actually discovered it to begin with.
And it could also be what, now we have light is carrying information, like fiber optics, so it could be a quantity of light as well.
Yeah, so if you want to see, if we're looking at how the information processing revolution came about, it's because scientists and engineers figured, oh, everything's already got this information associated with it, let's use it. You know, a particle of light, a photon, it can have a bit of information, like if it's wiggling back and forth like this. So if I take, my Ray-Bans, I put it like this, photon wiggling back and forth like that, you can call that a 0. Photon wiggling back and forth like this, Ray-Bans like that, you can call it a 1. So all these, particles, physical entities have information associated with them And when we build things like quantum computers, all we're doing is just taking advantage of that.
So does that mean then that information is limited by the laws of physics?
Darn tootin'.
Another precise answer there.
Wow.
Let me turn to Chris Fuchs from Perimeter Institute. Can you give me an example of how the laws of physics allow us to do things with information?
Oh, well, yeah, I certainly can. But I think, actually, just to follow up on Seth first,
Okay.
I've got to tell you about the first time I saw Seth Lloyd in public. He was emphasizing at that time not that everything can carry information, but that everything can be used to compute. And to make this dramatic, I remember him pulling off his shoe and putting it on the overhead projector and saying, "You could even use this old shoe to compute." So when he says these things, he's serious about it. So what was your question?
Well, I guess an example a little beyond the shoe of how you can use the laws of physics to manipulate information and do new things with it.
Well, you can certainly do new things when one takes into account quantum mechanics. So how shall I say? Here's a lovely example. Something called quantum cryptography. The task that's set in front of two people, Alice and Bob, is that they'd like to share a secret. They'd like to communicate to each other privately. In the classical world, where there was no connection, at least no seen connection between physics and information, when they would send messages back and forth between each other, somebody could gather information and it has no effect on the carriers of the information. Well, in the quantum world, there seems to be a deep connection between the properties of things and the information that one can get about them. So, for instance, if you get information about something, it changes the system in the process. This leaves a trace. Alice and Bob can see this trace, and they can learn whether someone has listened in on their conversations. So that's one example.
Okay. Now, Dr. Susskind, how do you define information?
Well, I think I would call information everything that you need to know about a system to know what happens next. So, for example, if you had a bathtub full of hot water, what information do you need to know in order to know whether to get into that bathtub or not? Well, you need to know its temperature, you may need to know its volume, to know if there's enough water there and so forth. But that's a very limited amount of information. There's an enormous amount of information stored in the position and velocity of every single molecule in the water. If you really want to know exactly what's going to happen next, you need to know the position and velocity of every single molecule in that water. So there's an enormous amount of hidden information that you don't ordinarily see when you look at the bathtub full of water. That hidden information, the information that you can't see, is what's called entropy. And if you really want to know in detail what will happen next from any given initial starting point, you need to know all of the information, which means everything that can be known, all the numbers, all the velocities, all the positions, which are the maximum amount that you could ever know about that bathtub full of water. And if you know it, you could predict what will happen next. That's what I call information.
Now, how close are we? I mean, that sounds to me like a huge amount of information. How close are we to actually knowing that? Just in a bathtub full of water.
Well, usually when I get into the bathtub, I know the temperature and the volume, and that's about it.
So the physics doesn't seem to be playing a lot of
Right. There's an enormous amount of hidden information that you can't see, and it goes under the name of entropy.
But I want a definition here, the difference between what we think of as classic physics and quantum physics.
Yes. Yes. I think in principle it really is the same thing, but I'm afraid that to give you the sharp distinctions between classical and quantum, I would have to give you a course in quantum mechanics.
And we don't have time.
So, no, we don't have time for that. So I would suggest that you come to my evening course, which we call Quantum Mechanics for Old People. And about as many people here come once a week to find out what quantum mechanics is. It's also on the internet.
Okay, but okay, in general terms, as I understand it, in classical physics, you're talking about gross motions, like Newton's laws, put something in action, reaction. With quantum, I think of the very small, what's going on within the atom, within the very tiny world where things don't behave the way they do out here.
Yeah, the character of quantum information is a little bit different than the character of classical information. It's a little more coarse-grained. In some sense, it's not quite as detailed. The uncertainty principle prevents you from knowing all the things that one would think one could know classically. So it takes a little bit less information in a certain sense to know what the quantum state is doing. On the other hand, it again corresponds to knowing the enormous amount of microscopic information that's in that bathtub full of water.
Okay, let's bring Tony Leggett from University of Illinois into this discussion. How do you define information?
I think fairly similarly to what Dr. Susskind has done. As far as I'm concerned, information always has to be about something, and it has to be embodied in something. And so I think a typical example of useful information is a map. A map represents certain properties of, let us say, a city. Generally speaking, it does not represent all the properties, but it represents those properties that you want to know about at any particular time. And it represents it according to a particular scheme. In this case, it represents it on a two-dimensional sheet of paper. We can imagine that in future, and this may intersect with some things come up later in this discussion, we may actually in future have three-dimensional holographic maps, I would think, but right now at least most of our maps are two-dimensional on sheets of paper. So I think every example of information has this character. It has to be about something in the world. It's got to be engraved or embedded in something in the world. But of course, the way in which it's embedded may differ enormously. Presumably, the fact that I'm talking in Waterloo this evening is something I'm conscious of. Presumably, it's embedded in certain neurons of my brain. I don't think, as far as I know at least, we have right now much idea of how exactly it's, as it were, engraved, if indeed engraved is the right word, maybe a totally misleading word. It may be embodied in more abstract things like rhythms of my brain and so forth. I think we just don't know, but I think it always does have to be embodied in some physical object. And I think there's a famous statement by Prof. Landauer, which says that information is physical, and I take that to mean that it has to be, you don't get your information free, it's always got to be embodied in something.
I think a better thing that Landauer could have said is information carriers are physical.
Yes.
That would capture your
Well,
point.
it would, yeah.
Dr. Susskind?
Yeah, let me completely disagree with you.
It was almost
Not at all.
getting.
Let's just clarify a point. For example, the information that Waterloo is north, is it, of Kitchener? Or is it south? I don't
Yes,
remember.
north.
But that information is not contained on map. That information is contained in Waterloo and Kitchener. Your map and my map might actually be different, and we don't know that until we look at the maps. And all the information on the map is that my map says that Waterloo is north of Kitchener, and your map may say something different. The actual information about the fact that Waterloo is north of Kitchener is contained out there on the surface of the Earth, where Waterloo and Kitchener are.
Is there any information that's not physical?
No.
No.
Yes.
No. Oh, that's
Oh yeah?
There's a lovely phrase I like by one of the inventors of Bayesian probability theory, who says probabilities do not exist. And by that he meant to capture the idea that there's a distinction between the world as it is. There's Kitchener and there's Waterloo. And you don't even have to say the word information to put one north and one south. You can just say there's Kitchener and there's Waterloo. And then there's what someone knows about it. Oh God, I can't remember whether Kitchener is south of Waterloo or east of Waterloo. And you look on a map, or you actually look at the things and you get surprised. And then because you're getting surprised, you're getting information. So just like the probabilist said, probability does not exist, that means it's not out in the world. I would say information's not out in the world, it's in your head. Well, the stuff out in the world's out in the world.
So let me just try to summarize what we've heard so far. And this is hurting me to do this. Because information can be little packets of electricity or quanta light that you can measure that we move from here to there. It can be in everything, including a shoe. It can be classical in the gross sense, or it can be in infinitesimal detail in the quantum world, where you may or may not know all of it, but you can predict the results if you try, maybe. Or it might be a map that's arranged in some configuration that you can try to push your way through. Is that generally what we've said so far?
Yes.
Thank you. Okay, sure. Okay, so let's move into what we can do with information. And Dr. Lloyd, I understand you were actually a consultant for the movie The Matrix.
No, for the movie The Physics of the Matrix. It was about
Physics. You're right, the physics of the Matrix.
There you go.
And you were also on my show on Quirks and Quarks talking about your book, Programming the Universe. So,
kind of you to mention it.
so is the universe really like the Matrix, a giant computer program that we're actually living in?
Do you want the short answer or the long answer?
Medium would do well.
Okay. All right, so I'll have to average them. Well, the short answer, of course, is yes. I mean, it was established 150 years ago that everything contains information, and that every atom has bits around. Every time they collide, these bits are flipping. This table, this glass of water, this shoe, they're just full of information, and they're processing it right and left. I guess it's a boot. So, yeah. So, the short answer is yes. But then, if you actually want to, but that's something that's really not very controversial. The time to object to that was around 1900, and people failed to. So that's pretty well established.
But what do you mean when the universe is a computer?
Yeah. So there's more. You could say, okay, it's processing information at its most microscopic levels. Therefore, it is a computer. That's good enough for me. But you might also want to know, okay, the universe is a computer. Why isn't it running Windows? Well, maybe it is.
Windows 14 billion.
Well, I would prefer to run Linux. Actually, that would be. I'm a more an open source person for this. But in fact, now we actually know the universe can do stuff like that, because my colleagues and I, for now more than 12 years, have been building quantum computers where we actually build computers that store bits of information on individual atoms. One atom, one bit, to paraphrase the U.S. Supreme Court, at least for the moment. So, yeah, so we can actually build them, and indeed, everything out there that we look at, when we look at it close enough, it's computing. So.
Well, give me an example of a universal computation.
We want the universe as a whole.
What's the universe computing? Like, give me an example.
Oh, well, it's computing itself. It's computing you, for one thing.
Is the answer 42?
You gave it away.
Of course, you know the answer. I want to know the calculation.
Yeah.
Well, what do you mean by that?
Well, so you could think, if you want to think of the universe as a computer, and as I say, it's a scientific fact. It's not really a metaphor. Then the universe is computing everything that we see. This table is being computed by the microscopic motions of these atoms. Lenny's bath, they got him warm and clean for this evening. That was the result of that computation. So everything that we see is a result of this computation.
So you're saying just because things are happening, atoms are spinning and molecules are jiggling and planets are orbiting stars, that's a computation?
Bits are flipping.
Bits are flipping.
They can all be described in terms of how bits flip.
What's the rest of the panel think of that?
What would be an example of a process which is not a computation?
Yeah, good question.
Maybe let me take a shot at this too. Maybe 150 years ago, people might have said the universe is a clockwork mechanism. What is the idea that the universe is a computation have that old idea doesn't have?
Well, yeah, it has the idea of information built into it. I mean, of course, you could easily accuse me, as I think you vaguely are, of saying, oh, well, we're in the midst of this information processing revolution. I own computers. I actually build quantum computers. Therefore, I think the world is a quantum computer, right? That's a perfectly reasonable accusation. That's why I was at pains to point out that this discovery that the universe is at bottom processing information was actually made by a bunch of people like Maxwell, Boltzmann, and Gibbs, who had no notion of computation at all. Yet they inadvertently almost discovered the fundamental laws of information theory.
But could you pose the whole idea without saying the word information? Could you say the universe is evolving according to some dynamical laws? It's doing it deterministically, it's doing it reversibly.
Oh yeah, absolutely.
Could you do that without saying the word information?
Yeah, you could do that.
Then what does information add?
Well, so you could also say your computer is just evolving by a set of dynamical laws, or for that matter, your brain is just evolving by some set of dynamical laws and no information is being processed. But I'm not going to say that because that would be the insane thing.
Well, sure, the universe is a computer. Anytime a system evolves according to a set of mathematical laws and goes from one state to the next according to any kind of mathematical laws, you can say it's doing a computation. What is the software? The software is the laws of physics. What is the hardware? The hardware is matter, the things that things are made out of. But, you know, there are some things that a computer may not share with the universe. For example, I have no idea if there's a programmer. I have no idea if there is a purpose to the computations. Most computations have purposes. I don't really think, although I don't know, that there's somebody waiting around for the computer to do its computation, waiting for the answer. Another interesting question is it ordinary computers, you can change the software. You can change the software, you can stop the computation, change the software, and have it do something else. As far as I know, there is no evidence that it's possible to change the software of the universe. So there are some elements which are really, really absent, or at least I think they're absent, from the universe that we would ordinarily think of as part of a computer. I'm not sure there's any good sense in which there are well-defined circuit elements, well-defined switches localized in space at definite positions, which switch on and off the way they do in a computer. In fact, I think there are good reasons, and we'll come to them, I think, to think that that's not the case. So, yes, there are elements of being a computer, and no, there are elements in which it's not a computer.
Or there could be other universes running different programs.
And there could be other universes running different programs. But I don't think anybody's going to stick their finger into our universe and suddenly change the software. Or at least there's no evidence that that will ever happen. So in that sense, it is different than a computer.
You mean you're saying that our universe is unlikely to crash at any moment?
Oh no, it's very likely to crash, I think. I think my president is almost guaranteed that.
Well, I've also heard the universe defined in musical terms, the harmony of the sphere, the music of the spheres, and that there are harmonics out there that you could describe in musical terms. But Dr. Susskind, you have another idea that instead of it being a computer, you have the idea that perhaps the universe is a hologram. Tell me about
Well, first of all, you say I have another idea. This is a mainstream idea in physics. This is an idea that many, many people have contributed to, and is now a very, very robust idea in physics. It's practically a tool of physics. Do you want me to say what it means?
Yes.
Do you want me to begin by saying what a hologram is?
Sure. Well, I think of it as a three-dimensional picture that you get on a film, and
It's a technique of storing three-dimensional information on a two-dimensional surface. Short answer. We've learned from black holes, from black hole physics, that the information that falls into a black hole is really, in some other sense, stored on the surface of the black hole, on the horizon of the black hole. The number of bits of information that can be stored in the black hole is no larger than the area of the surface of the black hole. And so in some way, everything that falls into a black hole, the full volume and all of the detail inside the black hole is completely coded by what you can think of metaphorically as a hologram stretched out on the horizon of the black hole. Now, interestingly enough, you can remove the black hole and you can simply think about, for example, the space in this room. Think about all the people sitting there. Everybody is composed of some bits. The rest of the room is composed of the bits. If you ask how many bits can this room store, you might think that the number of bits that the room can store is proportional to the volume, the number of cubic whatever it is that describe the volume of the room. But in fact, what we've learned from thinking about black holes and horizons is the capacity of this room to hold information is proportional to the surface area of the walls. So it's almost as though the capacity to describe the information in this room was described by a hologram composed out of a film on the surface of the room, the walls of the room. But then if you go out and look carefully at the walls, you won't find any hologram there, because the walls of the room are part of the bigger system, namely the building. And so if you think a little further, you'll say, oh, the information in this room is stored on the walls of the building. But then if you go a little further, well, I don't know what comes after the building.
The planet.
The planet and so forth. But the main fact is that the maximum amount of information that's stored in a volume of space is somehow proportional to the area of the boundaries of the region. And that suggests that in some funny kind of way, perhaps metaphorically, the universe or regions of space are described, roughly speaking, as holograms. Holograms that can change with time, and so things can move around, and quantum holograms, but holograms.
Wow. Oh, but as I understand black holes, they keep drawing more and more material into them, so can you overload that information? What happens if you put more information over?
No, that's the interesting point. It's taken a long time to sort that out, and it's been a big fight in physics, but it's finally sorted out. And the answer is no, you can't overload it. You can't overload it because the black hole also radiates. So the more information you throw in, if you wait, that information will come back out, and you can't overload it beyond the entropy of the black hole. The entropy is the maximum amount that black hole can hold.
Okay. I guess black holes can also get bigger too.
Yeah, they can get bigger, but if they're bigger, their entropy increases and their information increases.
So then are you saying that it's possible that the entire information of our whole universe is in a hologram around the outside of our known universe?
Well, I think when we start really talking about the whole universe, we get beyond what we really understand. But, right, we do get beyond what we really understand. But that having been said, yes.
Thank you. Dr. Leggett, we haven't heard from you. What do you think of these two ideas of the universe as a computer and the universe as a hologram?
Well, I think I would ask the question, if you say the universe is a computer, and you then say that has to be so, because every physical process is basically a computation, and then I want to know what you're excluding. What would it be like for something not to be a computation? And what has one added in that case by saying that it is a computation? And I think I do rather agree with the points that Dr. Susskind raised about the very specific differences, the fact that you can't just put in a new, with a humanly constructed computer, the whole point is that you can put in lots and lots of different tapes or whatever, or you can put in different things on the keyboard, and it'll run completely different processes. As far as we know, there's no such option in our universe, as you can see.
Now, I want to stay with you to get back at this difference between what we think of as classical physics and quantum, and there's the classic paradox of Schrodinger's cat. Can you tell me a bit about that, how it fits in?
Okay. So it's very well established at the level, in experiments which have been done for many years now, at the level of single atoms and electrons, that when, for example, a given atom can take two paths and then eventually get to the same point, all the evidence is that it doesn't look as if every individual atom chooses one path or the other. How do we know that? Well, we can basically argue that if each atom did choose one path or the other, then crudely speaking, the number of particles which got to the final point would be equal to the number which got there when they could only go by one path, and the number which got there when they could only go by another path. However, we find that's not the case. And in fact, very spectacularly, we find that when we can sometimes set things up so that we open one path, a certain number, a non-zero number of atoms arrive at a given point here. We shut that path and open the other path, again, a certain number of atoms arrive there. But when we open both the paths simultaneously, no atoms get there. So that seems to be saying that, well, the one thing we can, okay, what you say positively about that is perhaps a matter of taste. However, one can make certainly a fairly strong negative statement and say it does not seem to be the case that each individual atom went by one path or the other. That's, in some sense, that's the raw experimental facts and minimal interpretation of them.
Okay, that's indecisiveness in atoms.
Yes, yes.
Okay, but how does Schrodinger's cat?
So, well, we believe.
We're going to pause it for just a moment so we can break this up into smaller pieces. I'm going to continue in dispatch C. This is node 3, continuing in a moment.